Alright, hey guys, so today we'll talk about linear regression. So we talk about some of the fundamentals and then the optimization algorithm as well. So let's dive into the agenda, which you can see here. So we give a small introduction, talk about some of the fundamental concepts, assumptions in that particular model, then understanding the data, the cost function, the optimization algorithm, how the optimization algorithm links to the cost function, and how it links to other machine learning models, and then a small wrap up. So here, let's talk about the introduction. So what is linear regression? Linear regression is essentially you have your linear equation and you want to make a machine learning model out of your linear equation. So it assumes linear relationships. And why you should learn this, it's one of the most basic machine learning models, but once you understand it in depth, it makes learning all the other algorithms much easier. So what is the fundamental concepts? So here you have the equation, which is y equals beta 0 plus beta 1 x. Y is your dependent variable, x is your independent variable, beta 1 is your inception, and b1 is your slope, and then the coefficient in front of your independent variables. Now let's talk about the assumptions, which are actually very important, because yes, linear regression is an easy model, but one of the reasons it's easy is because we're making a lot of assumptions. So one of them being is linearity. So there's a linear relationship between your independent variables and your dependent variables. Another one is that your independence of errors, so that when you see different errors or different residuals in your, once you perform your machine learning model, is that they're all independent to each other and they don't relate to each other, and you can't make correlations from those. Another one is the homoscedasticity. I think that's how you pronounce it. I did Google it twice. So that basically means if across your independent variables, so in this case your x, when you look at different observations, the spread of the errors, the spread of the residual is more or less the same. So you expect like basically these kind of horizontal lines on your residuals and not something very big on one side and then very small on another side. So that's why we assume a constant variance of those. And the last but not least, we are talking about that the errors are normally distributed. So once you observe an error, you assume that most of them fit into the bell curve, so it's very close to zero, and then the more extreme errors are more rarer to find. Now, that's pretty much all on the assumptions. We'll dive into those a bit later. Now, let's talk about understanding the data, which is pretty much data collection and then visualization. I did not want to focus this presentation on that. Pretty much, yeah, get your data, understand it, and that's all it is. Next, we'll talk about the cost function. So in linear regression, the standard cost function is your mean squared error, which looks like this. And essentially, it's just the average of the squared differences between your observed value and your predicted value. So here, y1, if you can see that, yi is your observed value, and here is your predicted value. So it's just, that's your cost function, and you want to minimize it. So you want to make sure that's as small as possible. And another thing is in mean squared error is that it penalizes large errors a lot. Now let's talk about the optimization algorithm, which in linear regression we use OLS, so that's ordinary least square. That's also the optimization algorithm used in the scikit-learn linear regression class. So you can see, if you go on scikit-learn and on linear regression, you can see that being used here. And a how it works, basically it's a closed form solution. That basically means you need to do some matrix manipulation and some computation, and then you get the optimal value for beta 0 and beta 1. So there are no iterative process, and eventually this algorithm stops. And it's definitely going to stop as well. And yes, because there are only a finite number of computation, is very efficient for smaller data sets. Now, other machine learning algorithm, or you can also develop linear regression like this, don't use ordinary least square, but they can use things like gradient descent or stochastic gradient descent. So keep that in mind. So the optimization part is very important in most machine learning algorithms. Now, I made a new slide about how ordinary least square and mean square error link to each other, where essentially ordinary least square, the goal of that is to find the best parameters to minimize your mean squared error. And once you minimize it, you know you have the optimal solution possible. And one thing that's really good about linear regression is that we use a bunch of assumptions which we talked about here. Yes, you can see that. And OLS so works really good under these assumptions as well. So that's very nice. And yeah, so we want to keep that in mind. So if you change your cost function, just keep in mind if you can still use OLS or not, or even if it's the best one. Sorry, my video cut off. So yeah, how does this relate to other machine learning algorithms? So basically there are fundamental concepts like your cost function, your model assumption, and your optimization algorithm. And once you understand those for a simple case, which in our case is linear regression, you can easily apply those to more advanced machine learning models. And yeah, once you understand that generalization, learning your other models will make it way easier. So here let's do a small wrap up of this, where we talked about the introducing linear regression and the equations. We talked about some of the key assumptions. We discussed the cost functions and OLS and how they relate to each other. And then we also mentioned that in scikit-learn, OLS is the optimization algorithm. Yes, I'm sure there are other Python packages where you can have a different optimization algorithm, and many other models may use OLS, but also they can use gradient descent and stochastic gradient descent. And yes, thank you guys for watching.